we're going to look at lines and planes again. And I've got 8 questions, basically focusing now on planes and how planes interact with each other. So can you imagine that you had 2 planes, this one here, right? And a totally different plane, kind of coming something like this. Then one of the things that 2 planes could do is could they intersect on a line? Now, what other things could happen? Well, let's imagine. Can you imagine that you had 2 planes that never met each other? And the reason they never met each other was that they were parallel to each other, right? Technically, there is a third possibility. Couldn't both planes just be the same plane? In other words, they're embedded in each other. Right. And the reason that could happen is that the equations of planes are not unique, just like equations of lines are not unique. So you may see 2 equations and think because they have different coefficients of x, y, and z, and they're equal to a different number, that they represent 2 different planes, when in fact they could be identical planes just with different equations. So let's look at how we could find out some things. Take this situation, right? They intersect on a line. I would like to find the direction vector of that line. So how do you think I might do that? So I give you the equations of 2 planes, and I'd like to know the direction vector of the line of intersection. Any ideas? Well, if you imagine the green version of this line, right? If you take the plane that's normal would look something like that. Wouldn't its normal be perpendicular to that line? And if you imagine the purple guy, right, purple plane, wouldn't its normal be also perpendicular to that line? And so we want a vector, a line, that's perpendicular to 2 other vectors. And I'll call the red one N what? N1. And I'll call the other guy N2. So you find the cross product of the normals of the 2 planes. So if I wanted to find the direction of that line, right, the direction vector of that line, I'd find the cross product. So let's make up an example. Suppose you had this fella. Right, that's what a plane looks like, right? 2x plus 3y plus 2z, right? That's the kind of equation, and that's going to be my first plane. And let's suppose that the second one was that guy, right? So if I wanted to find the equation of the, not the equation, the vector v, the direction vector v, then I would find the 2 normals. Now, you can actually, from the equation, it's not that difficult to pull out what the normal vector would be. Wouldn't it be 2, 3, 2, the coefficient of x, y, and z? So that would be 3, 2, 3, 2. And the second one, it would be 4, negative 1, 1. And so the direction vector of that line would be the cross product of these 2 guys. So let me set up that guy. It's going to be I, J, K. 2, 3, 2, 4, -1. That fella. It's going to be so many I's. Take away so many J's. Plus K. Okay, if you go major 3, take away -2, that gets you 5. If you do the middle one, it's 2, take away 8, so it's -6. And -2, take away 12, which is what, -14. And I have 5 plus 6, -14. So if two planes intersect on a line, the direction vector of that line can be found by taking the cross product of the normals to the plane, right? The normal vectors to each plane. Pretend just for a minute that I did that and I got our friend the zero vector. What do you think that result is telling me about how these two planes are intersecting with each other, or not for that matter, how they're interacting with each other?
Is it that they're embedded?
Or parallel? So you might say, well, how do I find out which one it is? You do a test. You pick any point you like on the first plane, right? Just find any point that works, and you see if it's also on the second plane. Now, let's just pretend that these two planes actually gave us the zero vector. So you might say, well, how do I find a point on the plane? Since you can pick any point you like, let's take this fella here. Let's pick x is 0 and y is 0, right? Pick zeros. Now, won't that make 2z has to be 10, so that makes z has to be 5. That's how I found any point, just any random point I want. Just pick a couple of zeros and whatever's left is the third guy. Now, I would test this point, I'll call it P. Now, it's 4 lots of 0, take away a 0, add 5, 5. And the answer is, in this case, it was yes. Great. So what does that tell me? If this was here, if your two planes were parallel, wouldn't a point on the first plane never be on the second? If they were embedded, right, if they were the same plane, wouldn't a point on the first one have to be the same fixed point on the other? So that's what your test is. And if you get yes, they are, you're looking at embedded. And if you say nope, they're not, you know, that one doesn't fit this one, then you're looking at parallel. So far, so good. How two planes interact. Still working on how two planes interact. Let's suppose we know that they're not parallel. But I would like to know, how am I going to phrase this? Yeah. Do they intersect at 90 degrees? So I know they intersect, right? I know that they intersect, but visually, if this is one of the planes, I'll need cardboard. Imagine this is one of the planes and this is the second plane. Can you see that they may meet at right angles? Right? So how do we find out if that's the angle that they meet at? They will meet at some angle, right? They might meet at 30 degrees, right? Might come in quite sharp. They might be at 90 degrees, right? They won't be 0 degrees because that would make them embedded or parallel again. So how do we find that out? Well, it's all to do with normals again. And it is this property, the angle between the two normals is the same as the angle between the two planes. Oh, so if I want to find out what angle the two planes, cross each other at, right? Do they cross each other at 30 degrees or 90 degrees? Then I just need to look at that. So let's pick some vectors, some planes. There's my first guy. There's my second plane. And I want to know at what angle do they intersect at. The first normal is 2, -1, 2. That's this guy. The second normal is 3, 11, 4. And now I just need to figure out what do they do. Well, don't we know how to find the angle between two vectors? Isn't that the dot product's job? So the cosine of the angle between these two vectors is their dot product divided by the magnitude of the first vector times the magnitude of the second one. So what do we get? 2 times 3 is 6. Take away 11, add 8. Square root of 9, 121, 130, 146. And theta then will be the inverse cosine of 14.3 over this lot here. You know, in the homework, when they asked for the exact value, they wanted you to write this thing down. And typically we want degrees, so I'm going to make sure that I'm in degrees right now, which I am. Inverse cosine. Here we go. 3 divided by a bracket. Square root of 9, which I guess I could have called 3, but I forgot to. Times the square root of 146. And hope that's enough brackets. And the answer I get is 85 degrees roughly. Now, if it had been 90 degrees, wouldn't I have found that out when I'd got to that bit? Because wouldn't that be 0? If the dot product is 0, the angle is 90. You get that for free. Any questions about two planes interacting? The direction vector of the line of intersection, if it has one, or the angle between two planes, which is what we've just done. Have you noticed that everything uses the normals of the vectors? So if you're trying to figure out what the heck something does, and it's involving planes, figure out what the normal vectors are doing, because that's probably the answer. Okay, let's see what we got. Okay, I'm going to check what we've just done. Okay, the questions that we've just kind of done are 1, 2, 3. 1, 2, 3, and 4. So the things we've done are covered in the first 4 questions of your homework. So let's look at a question 5 and see what's going on here. we are being asked to find the parametric equation of the line of intersection, two planes. And the two planes are x take away y take away 6z equals 1, and 6x plus y take away z equals 3. So I'm making no attempt at being realistic. But can you imagine what we want to know is the equation of this line, right? This green line. You only need to know two things to get the parametric equation of a line, right? Two pieces of information that you need to get the parametric equation of a line. Anybody want to tell me one of them, or even both even? What do you need to know?
The direction vector?
Correct. What's the other thing we need to know?
A point.
Correct. So I guess I'm going to call x naught, y naught, z naught on a line. Right, if I can get those two things, aren't we pretty much the question's over with, right? Now, we've already talked about how to get the direction vector. Can you remember that that was the cross product of the two normals? Okay, so we'll call this guy 1, and right, we'll call this guy 2. So the normal for 1 is 1, -1, -6. And the second plane, guy I'm calling 2, it's a 6, a 1, and a -1. So far, so good. Right. Now, I want to get the direction vector, which is basically going to be my I, my J, and my K. And it's 1, -1, -6, and 6, 1, -1. And it's going to be so many I's, take away so many J's, plus so many K's. Okay, so that's 1, take away negative, that gives me 7. That's -1, take away makes it a plus, so it's 35. And that's 1, take away negative is add 1 is a 7. So I am looking at a 7, -35, 7. And we have got that guy.
Isn't it positive 35?
Well, this is, let's double check this. This is positive, but remember you subtract the middle one,
Oh yeah, okay.
so
Okay.
it ends up being negative again. It's dead easy to lose those darn signs. We haven't spoken yet about how to find any point on that line, because that's a little bit trickier, because there are a number of different ways in which you can find any point on that line, right? So I'm going to show you one particular method. So you start off with the equation of both lines. And I'm just randomly picking, it doesn't matter. The equations that I've got are ugly. So will you trust me that when WebAssign does it, you'll probably get the 0.123. Because I've randomly just picked these digits out of the midair, do not be surprised at how ugly the point that I'm about to find is, right? Its coordinates won't be pretty, but it's the method we're talking about here, not the details, okay? So what you do in this question, we'll call this equation 1, equation 2. is that you choose X, Y, or Z to be 0. And it doesn't really matter who you pick to be X, Y, or Z to be 0. So tell me one.
Z.
Z gets a job, which means that this equation will now turn into a system of equations that we can use any technique we like. Do you recognize this system of equations from Math 94, 99? Pair of 2 equations and 2 unknowns. Can't you do the elimination method, sometimes called the addition method, and the other method's called the substitution method? This one's ready for the addition method, isn't it? I would say. So in the addition method, provided you have, as we do have here, the same variable but 1 plus and 1 minus, we can just add them and get that, which makes X 4/7. Now I know what X is. Oh, by the way, don't I already know what Z is? Because I picked it. So all I need to do now is figure out what Y is. How do you find Y?
Plug them into an equation.
Okay, so I'll plug it into this one. So X take away Y equals 1. So 4/7 take away Y is 1. So subtract 4/7 from both sides, you get that. That makes Y that one. Again, not the prettiest answer in the world, but it works. So I know a point on the line. Its coordinates are 4/7, -3/7, 0. I know its direction vector, at least that wasn't too weird, 7, -35, and 7. So the equation of the line, it's x0 plus at, y0 plus bt, z0 plus ct, where these guys are called x0, y0, and z0, and these guys are a, b, and c. So we get 4/7 plus 70, -3/7, take away 35t, and nothing at all, so I won't write it, plus 7t, and that is the equation of the line of intersection of those two planes. Okay, I was not too bad, right? It could have been a lot worse, right? 4/7 and -3/7. So far, so good. Right. Now, if you want to write the equation down in what's called its symmetric form, someone sent me an email saying they weren't sure what that was. That's what an equation looks like in symmetric form. So it's really 3 things equal to each other. The only other equation I know that looks like this, and this has nothing to do with it, doesn't the sine rule look like that? You know, sine over A, sine B over B, sine C, it's 3 guys equal. Now all you do is you plug in 4/7, and you put it over 7, and then you do that guy, but taking that guy away makes it plus over -35. And then you do this guy, which is Z, take away nothing, so it's still Z, over 7. And that's what it would look like in its symmetric form. Are we okay with the equation of a line in its usual format, or in this new guy called symmetric form? Right, problems, and they are big, and you can't really get around them. You know the equation of a line is not unique. Right, we've talked about that before. If I had decided, because I wanted to make x equals 0, wouldn't I end up with a different point on the line? And if I'd chosen y equals 0, wouldn't I've ended up with yet a different point on the line. In fact, if you've been really awkward about it, couldn't I've picked z equals 22 because I just felt like it and get yet a third point on the line? Well, won't that make x naught, y naught, and z naught different each time? I think WebAssign, although it's probably good, might not be able to pick your one as one of its choices. So you could be doing the question correctly, but WebAssign says, it's not one of the answers I thought was going to happen, and just ding you. So that you just, if you're comfortable that you've done it correctly and you've done your 3 shots and it's killed you each time, because you don't really want to do the question again with a new point. Agree? That seems too much work. If you're comfortable with your answer and it just dings you, I guess you don't need to do it the other 2 times. You send me an email saying, this is my answer. Am I correct? And if you are, I just go in and give you the points. That's the only workaround I know. Theoretically, isn't there an infinite number of equations to any line? Because you could pick any point at all, right? There's an infinite number of them. Also, I just thought of this. Do you know if I switch places with these two, won't I get -7 plus 35 -7? And won't that generate a totally different set of also correct equations for that line? Right, where basically everything changed signs. So just live with it, right? Human beings are good. I can look at something and see that Noah's answer is different from Sam's, but Noah's and Sam's are the same straight line. They're just different equations. I don't think software, at least WebAssign software, is good enough to do that yet. So I've ranted on too much about that, but that's fine. And the other questions are really versions of this. Finding the equation of the line of intersection. Are we good? Right. Anything else I need to mention, or can we move on? Do you want to see another example of the equation of the line, or is this template, the one we just finished, good enough?
Yep.
Okay, let me move on then. So we are going to start a new chapter. Should be a drum roll or something for that, right? A new chapter. And you might be thinking, well, 163 hasn't really been that consistent, because the first load was all sequences in series, and then we moved totally different place in the world and we did vectors and 3D stuff and planes and lines. Not enough, a lot of, compatibility there. So where on earth are we off to now? Has anybody looked ahead to find out?
Vector functions?
We are going to look at space curves, which are vector functions. But space curves is typically the name we're going to use. It's
Sounds cooler.
it does sound cooler. Makes you think of space, right? Spaceships. So let's do an intro before we go anywhere near, because we only have a short amount of time. And it gives me, I'm trying to hit the right button. I'm not even sure where I am now. Right, we're back to white screen. That's where I want to be. We're going to look at things called space curves. And the problem comes from the fact that essentially when you deal with 3D world, some of the things that worked in 2D just don't work anymore. So I want you to imagine that this is a curve in 3D. So it's coming, analogy. Can you think of an aircraft zigging and zagging in 3D space because it doesn't want to get shot down, right? So can you imagine this curve might be coming out and then going in, and going up and going down and doing all sorts of cool stuff. This is called a space curve. Now, you cannot describe a space curve like z equals 2x plus 3y squared. You cannot do that. If you try to do that, you would find out that you don't get a curve. What you get is a plane or a surface. It's more likely a surface, right? Some curved surface in 3D, not a line, but like like the top of a hill, right? And so this notation fails. You were hoping that we could just say, well, y equals f of x. Can't we just call it z equals some function of x and y, right? Won't that do a space curve? And the answer, it doesn't. When you do this, you end up with a surface. So how do you tell people all the points on a 3D curve, a space curve? You do it like this. You do it like that. Now, do you notice that I've written down the space curve in terms of a vector? And the vector is called r of t. And these are functions. So to give you an example of what that might look like, you might get, I don't know, sine t, t squared plus 1, right? That would be an example of a space curve. Now, when you plug in t, you will get a vector, right? So for instance, if I went and plugged in 0 for t, I would get the sine of 0, 0, and 0 squared plus 1. I would get this vector. These are called position vectors. And position vectors are the vector to that point. So if you can imagine this here was where t equals 0 is. It's that vector there from the origin to that point P. So isn't the position vector just the same as telling me where the point is in 3D space as a coordinate? Because isn't 0 to a vector the same thing as the coordinates of 0 to that point? Does that make sense? That although your answer looks like a vector, it's a very special vector. It's called a position vector because essentially what that vector is doing is telling you the coordinates of the point.
Is that an equal sign with 3 lines?
Yes, it means in math equivalent to. So it's not quite the same as equals to in the equation way of equals. Equivalent to means it has the same information, right? They are equivalent things in that sense. They both tell you the same thing. That's a vector, and this is a point. So although they're not equal, aren't they essentially equivalent to each other? So space curves are cool because space curves have now expanded our ability to do things in 3D. And we are going to do all sorts of cool things with space curves. We are going to differentiate them and integrate them and then try and figure out what the heck that means, but that's something else. We are going to find out where one space curve might intersect with another one. They probably won't, but occasionally they do. Can you imagine one aircraft might crash into the other if you're unlucky, right? Could happen. And we'll look at how you do that and all sorts of other things. But the first thing we're going to look at is how you draw them. I'll tell you how you're not going to do it, and you probably agree with me. You're not going to take a 2D piece of paper and do a big table, right? When t is nothing, what's the x, what's the y, and what's the z coordinate going to be? And then try and plot some points and then join them up and hope to God it looks something like the shape. Would you agree it's impractical and ain't going to happen? So it's software. And so Software is going to be our friend. And now I'm going to have to leave this and go in and find out where the heck I put it, because I had it and then I lost it. And now I found it. I've put this already on your, oh, we got a chat. Is that something important? No. I guess Jason is telling me he's here. Think. Okay, let's show you what that software looks like. I've put it on Canvas, so you'll be able to get it yourself. It's CalcPlot 3D. And when you're doing in CalcPlot 3D, hit this guy and hit space curve, right? And X of t, Y of t, Z of t. Now, and this one's kind of cool. And can you see that the t values are negative to positive? And t is a good variable. It's a dummy variable that you use in parametric. And one of the reasons we like it is that it can represent time. So it doesn't just tell you the path of the object, but if t equals 10, it says this is where it is at the 10-second mark. Have you noticed, isn't that the exact same notation that we use for straight lines in 3D? So aren't straight lines in 3D just a particular space curve that ain't that curved? So here is cosine t, sine t. I wonder if I can make this bigger. That might help. Well, it makes this bigger. It doesn't change that, but that's something. Right, so you type in your guy and you get the space curve. And it's even cleverer than that.
They have a magnifying glass with a plus and a minus over on the left-hand panel.
Oh, thank you. Whoa. There we go. Maybe a plus. That's kind of cool. Now, when you draw a space curve, and although this picture doesn't show it, there is a direction to a space curve. And basically the direction is which way along that, that's a helix, by the way, that shape, do you travel? And so you either have the arrow going right or you have it going left. And so if you wanted to know what it was, wouldn't you just figure out where it was at time 0 and where it was at times 1, and it's going to continue in that direction. So it either goes, I'm saying right or left, I'm not sure if clockwise, anti-clockwise. Right, can you imagine the curve could be going this way that I'm pointing right now? So what you would do is you put a little arrow that looked like this. See the little arrow going like that? And that would be piece of the information. This cell is called a helix. If you look at it from a certain orientation, do you see it's basically a circle? If you look at it on this side, it looks like a slinky, doesn't it? Little spring. Very common shape. Now, you can play about with things, but if you ever see a cosine and a sine, and there isn't any multiples to them, right? It's going to be some version of a helix. So let's change this guy and see what we can do. Let's do t, not very interesting. Let's do 2t plus 1. And let's do 4 minus 3t. What do you think that should be? Yeah, let's find out. Oh, click off. Hey, why aren't you changing?
Do you have to click that graph button?
Show me it.
Above the add to graph, there's a little thing that says graph. Is that a button to click?
Okay. Nope. Oh, there it is. It was there all the time. It's not quite visible on the window that they've got, but you can play about with that and make it. I guess I could make this close
You can zoom out.
Let's browse. Right, let's go. There you go. Can you see it now? Of course, it goes on forever. Let's play about with this. Is kind of fun. I like doing these things. I'm hoping that it's taking that one or that one. That one. That is amazing. Not convinced. Oh, that's much prettier. Ah, do you see that guy looks like? I don't know if I zoom in too much, I'll miss it. There. That is a very weird space curve. They all have, I mean, I don't know what I was playing about with there, but that was kind of interesting. Let's just keep these two simple. Make sure that I'm really doing the graph. There we go. And I should be able to. There we go. Can you see a really boring ripple? Can you imagine then that you could really generate all sorts of movement in 3D space in the form of space curve? And that all these movements can be done, thankfully, with the graphing calculator, graphing software. And there is a fair number of homework questions where you would be expected to draw the thing, and it's one of those, here's 4 pictures, who am I kind of thing. Well, can you imagine that's going to be just go to CalcPlot 3D and say, yeah, the one I've got, if I change the window a little bit, looks like that one. They got this little thing called Animate, so here goes. Right, do you see that blue line that they've added? That is your position vector. Do you see how it ends up being from the origin to each point? So if I do that again. So what you kind of get the feel of is the movement of that object. And so you can tell which direction this object is moving, and would you agree it's moving, at least in this orientation, from left to right. Now we are going to steal some thunder.
You know what? That actually had a place for you to put in a direction arrow.
It does. Did I just miss it?
Yes.
Yeah, I'm not used to this, to be honest. Play about with it, have fun. Find out what Kathy was saying, that there's a button for putting an arrow on it, so
Yeah.
takes care of it. Right, so stealing thunder, what do I mean by that? Well, here is a space curve. If you want to find the derivative of a space curve, what would you think you would do?
Find the derivative of each of those.
Wouldn't it be very nice if all you did was differentiate each one separately? And the good answer is that's exactly what you do. Kind of interesting. If you integrate a space curve, you won't get a number like 42. It will not be a scalar. It will also be a vector. And if the world was nice and everything was the way it was meant to be, would you agree that the way you should do this is integrate each term separately? So if you integrate a sine, you get a negative cosine. You integrate this one, you get a power rule. It's a 3. It's a square. And you integrate this guy, you get e to the 2t. Right, a linear shortcut method. What do you get if you integrate e to the 2t? What's missing?
Where did the negative cosine come from?
Integrating a sine gets you a negative cosine.
Right, I was
Integrate.
going the wrong direction again.
It's so easy to do. Right, what do you get if you integrate e to the 2t? You get e to the 2t times something, don't you?
Times 1/2.
Times 1/2. Now, I'm putting a little plus c here and a plus c here, but that's not right. It's almost right. Do you know when you integrate and there's indefinite, you have a plus? If you write plus c plus c plus c, aren't you making the assumption that they're the same unknown number? In technical terms, that should be a 1, that should be a 2, and that should be a 3. So it's not uncommon for you to write the answer something like this. And C is a vector. And if you want to write out C, you would probably call it C1, C2, C3, but isn't it just less work to just call it C? What you're going to discover in the coming weeks is that space curves are very versatile, that we can do all sorts of cool things with them. But it would be nice to know what the meaning of these are, because they lose the two-dimensional meaning. Right, okay, time up. Say hi, everybody, and I'll see you all tomorrow.